Our Section 5 notes are all about using different logical arguments and operators. The first four are different logic operators when you have two statements happening and you want to decide if both are true, one is true, one or the other is true, neither is true, things like that. The first operator we're going to look at is not. In not, A is our example here. So what we're looking for in this Venn diagram where we have A, B, the region that's shared, and the region where neither of them is true, not A is literally everything that is not in the A circle. So let's go ahead and shade in everything here that is outside of the A circle. This includes the B, it includes the area on the outside. It doesn't include this overlap because A is a part of the overlap. The next one is and this is probably the most straightforward. Our example here is A and B. And A and B only occur in the area where the two circles overlap. And whenever you're thinking about Venn diagrams, generally this is what you'll think of is that overlapping region is A and B occurring at the same time. Third one is one you've probably never heard of, XOR, X-O-R. It stands for exclusive OR. So exclusive OR. And the reason it's exclusive OR is because it excludes the region of overlap where both occur at the same time. Now typically in English this is actually what we mean. I would like this or that, but not both. And obviously not neither. I want one or the other. So logical XOR would mean A and only A, or B and only B, and not the overlapping region. So not overlap. Fourth one down here, logical OR, is very similar. I would call it inclusive OR. So what we think of as OR in English is actually a little bit different than what we think of as OR in very mathematical or formal logic. Because mathematical OR says it can be A, it can be B, or it can be both. So if I say A or B, it's possible that both of them are true. When I say XOR, I'm being very specific that I only want one true at a time. So we have not, and, XOR, and OR. Jumping down, we have different types of arguments. First one is a direct argument. If this, then that. So if this, then that. So whenever the one thing occurs, you expect something else to occur. For example, whenever we score a touchdown, then we kick an extra point. So the statement would say, if a touchdown occurs, then the result or cue that we would expect here is that we go and we kick an extra point. So if a touchdown, then an extra point. Now some of you might be thinking, that's not always true. In fact, I know that you can do 2-point conversions sometimes in football where instead of going for a 1-point try, you go for a 2-point try. That would be a counterexample where you are disproving the main theory. So a counterexample is a specific example that disproves the argument. So in this football example we're using, going for a 2-point conversion would be a counterexample to the if touchdown, then extra point. This next box here, we're actually going to split this up into a couple things. This is a mistake in the way I set this up. There are two separate words that are very similar. And in fact, it's almost good that I made this mistake because it forces us to understand a little bit more about it. The first one we're going to leave as the converse, and we're going to adjust our definition as Q implies P. So the converse is literally just flipping the order of our statement here. So flipping order of Q and P. So in the football example, it would be if we kick an extra point, then we scored a touchdown. That would be the converse. It's just flipping your statement, your if and then around. The other word, though, if we split our box here, the other word we really want to talk about is contrapositive. C-O-N-T-R-A-P-O-S-I-T-I-V-E. Contrapositive. And what the contrapositive is the definition I originally had up here. Not Q implies not P. So whenever you do that, it turns out the contrapositive, if the main statement is true, the contrapositive is always true. For example, in basketball, you could say, if free throw is made, that implies scoring 1 point. The contrapositive would say not scoring 1 point implies not making a free throw. And that's true. If you do not score 1 point, you did not make a free throw. So the contrapositive is something in logic that is kind of strange. You flip the statement backwards, but you put not in front of each statement, and it turns out logically that that is always true. And here I just added that example here. If not 1 point scored, not free throw made. The contrapositive leads into indirect argument, where an indirect argument takes that not Q implies not P and allows you to then go backwards and prove the original argument. So let's start out with a different imaginary situation here. And let's say if raining, then grass is wet. So if it is raining, then the grass is wet. The indirect argument would be to say, let's flip it, if grass is not wet, what does that imply? That implies it is not raining. So the indirect argument would be to say the grass is not wet, therefore it is not raining. That proves the same thing as saying if it is raining, then the grass is wet. So kind of weird to wrap your head around at first, but if you think through different situations where something implies something else, you flip it to the contrapositive and put not in front of each, it will still continue to be true. Next word, biconditional. Another way of saying that is if and only if. And you might want to change that to and, not an. So if and only if. That is abbreviated IFF. If you're sick of writing it all the way out, you could just write IFF. Basically, it's saying that the conditional statement goes both directions. Going back to our last example, we could say free throw if and only if 1 point. So there is a free throw scored if and only if 1 point is scored. The way to verify this is to do it backwards and see what you get when you say the same statement backwards. 1 point if and only if, I'm using the abbreviation this time, free throw. Now, this statement is a valid biconditional. The reason for that is because if you score a free throw, that will give you 1 point. And if you scored 1 point in basketball, the only way that you could have done that is by making a free throw. Now, there's other situations where it is not true, both directions. If we look back up at our example with the raining, if it is raining, then the grass is wet. Well, if the grass is wet, that doesn't necessarily mean that it's raining. You could have the sprinkler on or something like that. So certain statements do not go both directions, but when they do, you can use this statement if and only if, and then you can write it as a biconditional. Then it says my statement is true both ways, both my statement and the converse. If we go back up to here, both my original statement and the converse are going to be true. Our last two words are inductive and deductive reasoning, and the main difference between them is the direction that you make your argument. Inductive reasoning takes many examples and then uses those examples to create a theory. Deductive reasoning, on the other hand, starts with a theory and uses that theory to create or confirm many examples. So jumping back up to inductive reasoning, let's say that we take a bunch of numbers that we know are powers of 10. So 10, 20, 30, 40, 50, and so forth. And we're going to look at all these examples and say, wow, I can come up with a theory that powers of 10 end in 0. So my theory is, by looking at lots of examples, that powers of 10 end in 0. That is inductive. So I take a bunch of ideas and then use them to create the theory. Deductive, on the other hand, goes the opposite direction. It starts with a rule. So it would say powers of 5, well, let's go back and go ahead and use the same example. Powers of 10 end in 0. And using that rule, that powers of 10 end in 0, I could say, well, I suppose a power of 10 times 1 is going to end in a 0. Power of 10 times 10 is going to end in a 0. 10 times 500. All of my examples should end in a 0 because that's what my theory is going to predict. So it's just two different directions of looking at the same thing. Inductive starts with examples, goes to a theory. Deductive starts with a theory and deduces the examples.